The next thing we need to do is thinking about matching symmetries. So we started with our conversation about symmetry with the idea that our field and our charge distribution are going to have the same type of symmetry. So let's now look at some examples of where the symmetry does not match or where it does match. And this is really meant to be just some examples. So we're going back to our infinite cylinder, and we need to think about a side view, and then we need to think about an end-on view. So remember, electricity, magnetism, fields, this is fundamentally three-dimensional, and most of us are really bad at drawing 3D. So the best way to do that is to do a side view or a top view and then an edge view. So just draw two views. And this is really important in particular for symmetry. So let's say that we don't know the shape of the electric field, and so we're guessing that it's this. So again, we have our charge, our infinitely long line of charge, and then we have this electric field. Now this might seem reasonable, but when we reflect it from left to right, notice that our charge distribution is the same. Nothing has changed about our charge distribution. But now, when we look at our electric fields, they do not look the same. This one's angled to the right, this one's angled to the left. And that doesn't make sense. If these two charge distribution pictures look identical, then the field should look identical. So this means that when you reflect it on this left-right symmetry, so we're reflecting on a plane that is perpendicular to the axis, that the symmetry of our field must also reflect. And so that, for instance, might tell you that, hey, our field actually needs to point straight out. If it has any sort of left or right direction, that won't be preserved under this left-right reflection. So then, another thing for the end-on, we can kind of have this lovely little pinwheel shape. And really what's happening is that instead of coming directly from the center, each of these lines is coming from kind of the edge, tangential. And normally we say that our infinite line of charge doesn't really have a radius, but in this case we're not saying it's infinitely skinny. So we're giving it a finite radius and saying that each of these lines kind of comes off tangentially. Now here, again, we can do a reflection. And now we're reflecting across the plane that passes through the axis. And now you see that here, like this line on top initially was kind of coming, up and out. But now it's coming up and out from a different place. Or if we say, where is it coming from here, right? That's kind of the better way to think about it. That if we say, what is this point here doing here, it's coming up and out. Now it's coming down. So we've again lost that symmetry. We've drawn an electric field using kind of these vectors or lines that doesn't have the same symmetry as our charge distribution. And so this is again what you can think through and why we think about these symmetries. There might actually be more than one type of electric field distribution or that you might draw, but it definitely isn't correct if it does not have these symmetries. So that's the basic idea. So these would be examples that are wrong because the field and the charge distribution don't match. So what's correct? Well, again, we've already learned about the electric field from an infinitely long line of charge, and so yes, it has to point straight out. Why? Because if we try to reflect along any plane, we need to not have it go pointing from left to right. And here, reflecting this, we get exactly the same thing. Here it's not quite uniform if you think about all of space, but as you move from left to right, your field strength doesn't change for, say, the same distance r. That makes sense because there's a translational symmetry. When we look end-on, we see that it points out exactly from the center. So if we imagine reflecting it along any of the planes, it's preserved. We can also imagine rotating it, and it's preserved. So you might say, I don't see why I need to know this. You've already taught me what this field looks like. But the idea is we're going to be using symmetry to think through fields and charge distributions that we haven't learned yet. And so this is why we kind of need to practice with something that's simple, and simple things well, things are particularly simple if you already know the answer. So now let's look at a different case, which is the finite rod. So in this case, we actually see the end. This is very important to note that it's a finite rod. What this means is that translational symmetry that we had before, we don't actually have that now. Because if I look at one point here, that's say right by the edge, I can go, oh look, that's on the edge. A point further over is in fact not on the edge. So we do not have translational symmetry. So let's just look at this first case, this first picture B. Now we have an end view and we have a side view. Again, fields are three-dimensional, so we need both views. Now, this end view looks okay. It has the rotational symmetry that we expect, because our charge distribution still has that, and it has the sort of reflection symmetry that we expect. And again, this is still going to have reflection along these planes that are the plane that the axis lies in. It's still going to have reflection symmetry there, but now it really only has reflection symmetry in the middle if we look end on. Notice that this reflection doesn't work. Why? Because here it's small, here it's big. So if we imagine taking those fields here and those fields there, our charge distribution looks the same, but now our fields don't. So that's definitely bad. So now let's look at the next one. If we start again at that reflection symmetry, we actually see that reflecting the fields over works. That's okay. But then when we come to the end view, we're back to the problem that if we try to reflect here, this one goes there, that one goes there. Is that going to be exactly the same? Because at the top, instead of pointing to the right, it would now point to the left. So this doesn't work. So again, that top one, when we think about kind of a full three-dimensional view, it didn't work due to one symmetry not being preserved here. The second one looked okay from the edge view, but it kind of had this weird rotation thing going on that broke the symmetry on the end. So neither of these work. Let's look at two more. Now here, notice that we have that good end-on view that has the rotational symmetry we need and the reflection symmetry we need. So both of them work on the end. Now, notice that they look different from the side view. So let's start with reflection. Is this preserved when we reflect? Now keep in mind that when we reflect this, it actually does become like that, right? So it's pointing in, we reflect, it still points in. So that seems okay. And if we imagine reflecting across this, this does become that. So this one actually looks okay from symmetry. Now, it doesn't have translational symmetry, right? This arrow does not become that arrow, but this part of the charge doesn't become that part of the charge because here we're at the end and here we're not. So even though this field distribution doesn't have translational symmetry, neither does our charge distribution. So every symmetry that we can think of for this charge distribution, the field has. If we come down here, we can again look at reflection and see that it works. We can look at reflection here and see that it works. And if we think about rotation, which is kind of hard to do in this view, you would actually think about it from the end, it also works. And so again, it doesn't have translational symmetry, but neither does our charge distribution. So that one works too. So this is actually really key. Symmetry arguments only get you so far. In this case, there are two different field shapes that actually have the same symmetries of our charge distribution. So we would kind of have to make a different argument to determine which of these two it is. So that's something to think about. But if, for instance, I didn't show you the charge distribution and just showed you this field, you would know that it would have this sort of kind of limited cylindrical symmetry. So again, symmetry is a tool, but it is not the only tool you're going to need in your toolbox.